The geysers are quiet this morning. Steam rises in slow, patient columns above the upper geyser basin, drifting into a pale Wyoming sky. Bison graze along the tree line, unaware that beneath their hooves, under nearly half a mile of rock, a chamber of molten silica and gas has been swelling for centuries. Tourists photograph Old Faithful. A ranger logs a routine seismic reading. Nothing on the surface suggests an ending. But 3,000 feet below the caldera floor, the mathematics of pressure have quietly shifted. A reservoir of magma, 90 kilometers long, stretches beneath Yellowstone like a hidden continent of heat. For most of human history, it has simmered. Occasionally, it has vented, hissed, bubbled. It has never, in the age of written record, done what it is capable of doing. This is the story of the last 72 hours. Not a myth, not a disaster movie fantasy, but a reconstruction built from seismology, gas chemistry, deformation models, and the geological memory of Yellowstone's 3 previous supereruptions, the last of which, 631,000 years ago, ejected roughly 1,000 cubic kilometers of material into the atmosphere. To understand what a 4th eruption would look like, science must first understand what happens in the hours before the ground itself gives way. The narrator does not exaggerate. The scale requires none. Deep beneath the caldera lies a 2-tiered plumbing system. The lower chamber, a hot, mostly solid mass of rock threaded with pockets of melt, sits nearly 20 kilometers down. Above it, closer to the surface, is a smaller, more volatile chamber, perhaps 5 to 15% molten by volume, saturated with dissolved gases, water vapor, carbon dioxide, sulfur dioxide. This upper reservoir is the one that matters. It is the pressure cooker. For an eruption to move from possibility to inevitability, 3 physical thresholds must align. The first is volatile saturation. As magma cools and crystallizes at depth, dissolved gases are squeezed out of the melt, unable to remain in solution. This is the same principle that governs a shaken soda bottle. Pressure keeps gas dissolved until it doesn't. In the 72 hours before rupture, models suggest this exsolution accelerates rapidly, gas bubbles nucleating and expanding by orders of magnitude within the chamber roof. The second threshold is roof failure. The rock capping the magma chamber is under enormous confining stress, but it is not infinitely strong. As gas pressure inside the chamber climbs past the tensile strength of the overlying rock, cracks begin propagating upward, not gradually, but in a runaway feedback loop. Each fracture reduces pressure locally, which triggers further gas exsolution, which raises pressure again, which drives the fracture further. Geophysicists call this a positive feedback cascade, and once it initiates, it is largely self-sustaining. The third threshold is the seismic swarm. In the final day, instruments would very likely detect thousands of small earthquakes clustering along the widening fracture network, a phenomenon called harmonic tremor, a continuous seismic hum distinct from ordinary tectonic quakes, caused by the resonant rush of gas and magma through newly opened conduits. Ground deformation, already measured in centimeters per year at Yellowstone under normal conditions, could shift to centimeters per hour. GPS stations across the basin would register the caldera floor visibly rising, in places by more than a meter, as the crust is forced upward like a blister. Gas emissions would spike correspondingly. Carbon dioxide flux from soil vents, already elevated in areas like Mammoth Hot Springs, would climb into ranges lethal to wildlife in low-lying terrain. CO2 is denser than air, and it pools. Sulfur dioxide concentrations would sharpen the acrid bite, already familiar to anyone who has walked the boardwalks of Norris Geyser Basin. Hydrothermal features would begin behaving erratically. Geysers erupting off schedule, some violently, some falling silent as their plumbing is disrupted by the shifting stress field beneath them. By hour 12, hydrothermal explosions, violent but localized blasts of steam and rock distinct from magmatic eruption, would very likely begin occurring across the basin, hurling debris hundreds of meters and carving new craters in what were, days earlier, quiet meadows. These are not the main event. They are the pressure system clearing its throat. At hour 0, the roof finally fails completely. What follows is not a single explosion, but a violent, self-accelerating discharge that geologists classify at the extreme end of the Volcanic Explosivity Index, a VEI8, the highest category the scale allows, reserved for eruptions that eject more than 1,000 cubic kilometers of material. The initial blast would be nearly instantaneous in human terms. Magma and gas erupting through multiple vents simultaneously as the chamber roof collapses inward, forming a new caldera in a matter of minutes to hours. Within the immediate region, encompassing much of Yellowstone National Park and its surrounding counties, destruction would be near total. Pyroclastic density currents, superheated mixtures of ash, gas, and rock fragments moving at speeds exceeding 100 kilometers per hour, with internal temperatures above 400 degrees Celsius, would sweep outward across the landscape, incinerating forest, structure, and life within tens of kilometers almost instantly. Beyond that zone, the danger shifts from heat to burial. Within a 500-kilometer radius, encompassing cities like Billings, Salt Lake City, and Cheyenne, ashfall would begin arriving within hours, driven by prevailing westerly winds. Ash accumulation of even 10 centimeters is sufficient to collapse conventional roof structures under its weight, particularly if the ash becomes wet from rainfall. Volcanic ash, unlike snow, is dense, gritty, and does not compress or melt away. Electrical grids would fail as ash coats insulators and shorts transformers. Water treatment systems would clog. Vehicle engines, drawing in abrasive ash through air filters, would seize within kilometers of driving. For the estimated hundreds of thousands of people within the most severe ashfall zones, survival calculus would center on shelter integrity, air filtration, and water security. Respiratory injury from fine ash particulates, silica-rich shards small enough to penetrate deep into lung tissue, would become a leading medical emergency, particularly for those with asthma or cardiovascular conditions. Livestock across the agricultural heartland of the northern plains would face mass die-off as ash smothers grazing land and contaminates water sources with fluorine compounds adsorbed onto ash particles, a toxin known to cause fluorosis in grazing animals within days. Farther out, the ash plume, injected tens of kilometers into the stratosphere by the sheer force of the eruption column, would begin circling the globe within weeks. Commercial aviation across North America would halt entirely, as volcanic ash is capable of melting inside jet turbines and re-solidifying on turbine blades, a failure mode that has already downed engines in smaller eruptions elsewhere in the world. This is not conjecture built from fear. It is the direct extrapolation of what happened during Yellowstone's last 3 super eruptions, layered onto a modern world of dense infrastructure, industrial agriculture, and continent-spanning air travel, a world with far more to lose and far less room to retreat. The immediate devastation, catastrophic as it would be, is not actually the eruption's most significant legacy. That distinction belongs to what happens in the sky over the following months and years. Sulfur dioxide injected into the stratosphere converts into sulfate aerosols, microscopic reflective particles that scatter incoming sunlight back into space. Following the 1991 eruption of Mount Pinatubo, a comparatively modest event, global average temperatures dropped by roughly half a degree Celsius for over a year. A Yellowstone supereruption would inject sulfur on a scale hundreds of times greater. Climate models built from studying past supereruptions, including Indonesia's Toba eruption roughly 74,000 years ago, suggest global cooling of several degrees Celsius sustained for multiple growing seasons, a phenomenon sometimes called volcanic winter. The agricultural consequences of such cooling would dwarf the direct casualties of the eruption itself. Shortened growing seasons across the northern hemisphere, combined with disrupted monsoon patterns and reduced sunlight for photosynthesis, would strain global grain reserves in ways modern just-in-time food distribution systems are not designed to absorb. The Toba eruption has, controversially, been linked by some researchers to a genetic bottleneck in early human populations, a hypothesis still debated, but one that illustrates the sheer scale at which supereruptions can act on the trajectory of a species, not merely a region. And yet Yellowstone's deep past also offers a quieter, more sobering counterpoint to catastrophe narratives. The volcanic system's 3 known supereruptions are separated by roughly 600,000 to 800,000 year intervals, and the geological evidence indicates the system is not currently primed for imminent eruption. Magma chamber melt percentages remain well below the threshold typically associated with runaway rupture. Monitoring by the Yellowstone Volcano Observatory continues around the clock precisely because the warning signs, when they eventually do accumulate, would very likely unfold over years or decades, not merely the final 72 hours reconstructed here. That final countdown, then, is less a prediction than an instrument, a way of making an almost incomprehensibly large system legible in human terms. Standing today at the rim of the caldera, watching the same steam rise that has risen for thousands of years, it is worth remembering that Yellowstone's silence is not evidence of safety. It is simply evidence of time, the same patient, indifferent scale on which the mountain itself was built, and on which, eventually, it will erupt again.